This is Creating Model Academic Enhancement School GMAT 41. You are welcome to our practical chemistry class. In this video, we are introducing quantitative analysis, that is titration, or otherwise volumetric analysis. And we'll start first by looking at the reagents, the apparatus we need, and of course the experimental setup. Is that okay? Now on the board here you have the apparatus you need, the burette, the pipette, the flat bottom flask, the conical flask. Is that okay? And then we have the reagents, specifically acid and the base you want to use for the neutralization reaction. And don't forget indicator which you need. The indicator helps us to determine the endpoint of the neutralization reaction. Now, before we move on, we want to look at what indicator is suitable for a given acid-base pair, solution. We want to carry out titration reaction using a given acid and a base. Which indicator would be preferable to use? Now, we have them on the board here. If the acid is a strong acid and the base is a strong base, any indicator can be used. So you can use methyl orange, you can use phenolphthalein. Most times, in terms of your practical chemistry practical titration, we usually specify and use phenolphthalein or methyl orange. Other ones like the bromocresol and thymol-blue, the rest of them, well, can be used, but specifically methyl orange and phenolphthalein are used most times. Now, if it is strong acid and weak base, or you use triazocarbonate 4 as the base, what indicator is suitable? Methyl orange goes for it. Then weak acid and strong base, phenolphthalein should be used. If it is weak acid and weak base, there is no suitable indicator. So you would have to decide based on experiment, the experience, rather the indicator to use. Now below here we have the diagram. The diagram for titration experiment. Of course, you have your burette that is clipped to the retort stand. The burette usually contains the acid solution. And then we have the pipette. This is your pipette. The pipette is used to suck base from the flat bottom flask. Usually you collect your base and pour into the flat bottom flask, and then you pipette the base by sucking using a pipette. This is the pipette. Is that okay? You have to suck the base to get to this point. Usually in the laboratory you see 20 centimeter cube or 25 centimeter cube pipette, as the case might be, whichever your laboratory has. Alright, now you can see once you have pipetted the base, the next thing you need to do is to add it to your conical flask. And then after that, you add either 2 or 3 drops of the indicator that you're using for the experiment. That is why here the solution inside this conical flask and is base plus what? Indicator. Once you have added the base to the flask and then add 2 or 3 drops of the indicator, what do you do next? Bring the conical flask below the burette containing the acid solution. You can see that. Then carry out your experiment. This is a clip. Look at it. It's a clip. When you hold and press it, it will open the burette and allow the flow of your acid into this base indicator solution. As the acid is entering, you need to shake the conical flask steadily, okay? Most cases, I suggest and prefer using my left hand to hold the clip. Is that okay? Right hand will hold the flask, that's the conical flask, while shaking it. Once again, it's usually ideal, although not a rule, but it's ideal to place a plain white paper between this conical flask and the base of this retort stand. Alright, the reason for that is for the white paper to allow for reflection. Is that okay? For the white paper to allow for reflection, for you to see a clear color change at the end of the neutralization reaction. In the next video, we are going to see formulas we need for calculation purposes in titration problems. Alright, now we want to talk about formulae that are necessary, okay, in titration experiments. You should get to know them. The first is concentration. Under concentration, we have 2 major formulas there. Concentration can either be mass concentration or it can be molar concentration. For mass concentration, you have the unit in grams per dm cube. So it's just like saying mass over volume, because volume is in dm cube. So you get the mass concentration. Then molar concentration is a number of moles per volume, so it's just like saying number of moles over volume. Both of them are concentrations. The only difference is that one is in grams and the other is in what? Moles. Now on the board they have two formula expressing that. This formula very important, so go through it. This formula gives us the relationship between molar concentration, which is also called molarity. Is that okay? Or concentration in mole per dm cube. It relates it to concentration in grams per dm cube. So take note. In fact, this formula is specifically used in cases where you want to get mass concentration. Is that okay? And then you know the molar concentration. Now we have another formula there we call the cover formula, just as a means of quick remembrance. And we have a CAVE over CBVB equal to NA over NB. Now I want to say this. Mass concentration has nothing to do here. This formula is specifically for molar concentration for this. So for example, if this molar concentration is for the acid, then you are actually talking about Ca. But if it is for the base, then you're actually talking of what? Cb. Let me quickly talk about Va and Vb, very important. Va is your average titer value, average volume of acid used. You remember after running a titration experiment, you get your table, you have the volume of acid used, the last row of the titration table. Okay, now you run the experiment, in most cases, first titer, second and third titer. So the volume of acids you use, first, second, third, add the 3 divided by 3. You get an average volume of acid used. That is your Vb, your Va rather. Then Vb is the volume of the pipette that you used to suck your base. Is that okay? And in most cases, the volume of the base, where you see the pipette used in the laboratory, could either be 20 cm cube or 25 cm cube, depending on the one you meet in your laboratory. Na and Nb represent the number of moles of acid and base in the reaction equation that you will see if you're running a titration experiment between hydrochloric acid and sodium hydroxide, for example. If you balance up the equation, you will see that the number of moles of acid to base will be 1:1. Okay, now other important formula number 2, we have the amount formula. There are 2 of them here. One of them is number of particles divided by Avogadro's number. Avogadro's number is a constant. Look at it. Then another amount formula is that which is mass of substance divided by what? Molar mass. N is number of moles equal to mass of the substance divided by the molar mass. Then again, percentage purity is another important formula you likely encounter in your titration problem. Is equal to mass of pure all over mass of impure times 100%. Once you've gotten the percentage purity, you can also get percentage impurity by subtracting this from 100. Then again, your water of crystallization is another thing your attention might be called to in your titration experiment. It's very simple. In fact, this is one of the most important aspects of your calculation in titration. Once you know this, these other ones can easily be determined. In talking about the water of crystallization here, you usually obtain it from the molar mass of that substance. And you know in this formula like here, you have the molar mass. Is that not so? Alright, so that's that. In the next video, we're going to see how titration table looks like and what is expected in completing that table. So now we want to look at how we fill up the table of value of our titration experiment. It's very important that we know about this. Sometimes we run this experiment in the laboratory and we may just end up wasting acid, but because we always want to go and make it up to this point 0. Now to start, you collect your acid and then you pour the acid into this burette. Usually you fill it up to the 0 centimeter mark. I just drew this thing to show the marks clearly. In between each of these, you have lines, about 10 small lines between. Is that okay? So you fill up to this point 0, which means your initial volume of acid you use. You can see the table, the arrangement, okay? The rough is to serve as a guide. In that rough, you record it so that you will know, all right, it is at this range, this value of acid used that I am expecting that there would be a color change, that I'm expecting that neutralization would have taken place. So if you fill the acid, okay, the burette up to the 0 centimeter point, then you come to initial volume of acid and then record 0.002 decimal. Is that okay? Then you now start running, you know. In the previous video, I've already explained how you hold the clip and then allow the acid to flow into this conical flask while shaking the conical flask and watching for a change in color. So when you start running your experiments and you're shaking, let's assume you notice the end point, dependent on the indicator you used, you know. If you notice that, oh, the color has changed, it has neutralized, you stop. Now let us assume that you ran, the acid you used was from this 0 cm mark up to, let's say, this point. Okay, let me assume that this point is 0.15 cm cube of the burette. Then you stop and come to the final volume of acid used and record 15.00. Okay, it's ideal you fill up everything first before completing this. This is just done by doing subtraction. But if you want to do your subtraction straightforward, it's your choice anyway. 15 minus 0 will give us what? 15. So the actual volume of acid that neutralizes the base in your rough is 15 cm cube. This is a guide. This is to tell that once you are approaching 15 cm cube, if you're running your experiment, once you are using up to or close to 15 centimeter cube of the acid, you should be very careful. Don't rush the acid again. In that case, you hold your clip, you close, you hold and clip, because just within that range, a drop of an acid may just affect the color change you are looking for. Is that okay? So that is the point. It will serve as a guide. Now, in the next experiment, what do you do? Now, I'm going to ask you, a burette reads from 0 to 50. If actually 15 centimeter cube volume of acid brought about neutralization reaction, and your acid at this point is at that 15 centimeter cube. Now, I'm going to ask you, do you think it's ideal to go and pour acid again into the burette to make it up to 0 cm cube? Is it ideal? Not at all. That is going to be a waste of acid, number one, a waste of your time, number two, and stress on you, number three. Why? If 15 cm cube brought about neutralization, from this 15 now to 50, do you know what is left? If you do 15 minus 50, what will you get? You get 35, is that not so? It simply means that the volume of acid left from this point to this point is 35 centimeter cube. It's enough to produce a neutralization for you. So don't go punishing yourself filling up. Is that okay? It's going to waste your time. Just run from there the second titration. Now, when you want to do the first titration itself, because this one is rough, it means that you are starting from this point for the first titration. Is that not so? So your initial volume of acid used will be 15.00, because this is where the acid was in the burette while you are about to start the second experiment, which is the first titration. Then you start running your experiment again. Titrate. Okay? Of course, you know the first one you obtain, the first solution of color change you obtain, you have to pour it away, rinse the conical flask with a base. Is that okay? Then again, pipette your base, add to it, add your indicator, bring it, and then continue the first titration. Now, let us assume that while you're rushing, this from 15, the thing is getting up to, let's say, 25 to 30, you know? You want to be very careful. Remember, 15 cm cube changed the color. So around that 25, let's say around the 12, 13, 14 volume of acid used should be able to change color as well too. So you need to be careful at that point. Okay, now let us assume that you ran this thing up to, let's say, the 29, and you saw a color change. It means that the final volume of acid will be 29.00. Do your subtraction, let's see. 29 minus 15 will give us 14. You see that, right? It means that 14 centimeter volume of acid changed the base or brought about neutralization. Good. Now at this point, if the acid is at the 29 centimeter mark, let's say somewhere here, 29 centimeter mark. Let's say somewhere here. 50 minus 29 will give you what? If you do 50 minus 29, what will you get? You're going to get there about 21. Is that not so? 21 again is sufficient to bring about color change. Remember, this thing is telling you that at least if you use up to 15, you should expect a color change. So 29 volume of acid left, or 21 rather volume of acid left in the burette is enough to run your second titration. So going to collect acid to make up to 0 again is a waste of time. Now, if you are to run from the 29 cm mark, let's say that it's at 29 cm mark, if you are to run from here, then coming here, your initial volume will now be 29.00. Then you start the second titration, which of course is the third in row, because remember the rough was actually first, but you don't count this. It's just a guide. Alright. Now, running from 29, let's assume that the thing got up to 43 and it stopped. And you observe your color change, rather. What will you do? You come to final volume and record 43. Let's say 0.5. Let's say it starts for 3.5. And then you're going to do a subtraction. 43.5 minus this. What will you get? You're going to get 0.5. Then 13 minus 9 will give us 4. And then this 3 minus, you have 14.5. So you see that? At this point, the acid is at 43.50 cm mark. So understandably, the volume of acid left is not enough to run the last titration. You can now get your acid and fill it up to a particular point. You mustn't fill up to 0. Fill up to a point at least that will be, you know that what is left in the burette is a kind of more than 15 or so. You can fill up from that 43, let's assume as you're pouring, allow it to get to 30. You mustn't fill up to 0. Once it gets to 30, you can run from there, because if the volume of acid in the burette is up to 30, what does that tell you? 50 minus 30 gives you 20 cm3. It means that the volume of acid in the burette is 20 cm3. Is enough to run to bring about what? Color change. Alright, let's assume now that we filled the burette up to the 30 cm mark. So I will come here and write initial 30.00. Are you seeing it? 30.00. Then start the last titration experiment. And then let's assume that when you ran, the thing actually got to, let's say, the 42. So your final, this will be 42.00 before you saw the color change. Do your subtraction, 0.21. So you see 12. In most cases, if you have this rough and after the first experiment, you might use your experience to fill up this one. Is that okay? So we are done with the table of values. Now we have these questions to solve, alright, using our table. Okay, this is a table generated from a titration experiment that was run already. The reaction is between the base potassium hydroxide and tetraoxosulfate 6, H2SO4. Volume of the base is 25 cm3, that's the volume of the pipette, and then the indicator used for the reaction is methyl red. Okay, we are asked to calculate the average titer, the molarity of acid, the mass concentration of the acid. Now, did you take note that we were given the molarity of the base, that is Cb, concentration of the base in moles per dm3. Look at it. We read this as 0.4 molar. It represents molarity. Okay, that is molar concentration of the base. Now, the first thing we need to do here is to write out the balanced chemical reaction equation for the acid-base pair. The reaction is between tetrasulfate 6 and potassium hydroxide. If you look at it, the equation is balanced here already. All you need to do is to pick out the number of moles of the acid and base. Number of moles of the acid is invisible 1. Okay, so you put it there. Number of moles of the base is 2. You put it there. Now, first we have to calculate average titer. How do we proceed? Average titer is simply equal to sum of volume of acid used divided by number of titration. And so here you're going to pick this plus this plus this. Okay, and then add them and divide by the number of experiment 3. If you do that, you're going to get 13.5 centimeter cube. We proceed to calculating the molarity of the acid. Now, if you're talking about molarity, you know that you have two formulas from which to choose from. Is that not so? One, the cover formula, and then the other formula that relates mass concentration to molar concentration. And of course, you use this second formula if you know the mass concentration. Then you can now use it to calculate the molar concentration, which is molarity. But for this problem, we do not know the mass concentration of the acid. We don't. Alright, it means that we can't use this formula. Look at it. That formula that relates molarity to mass concentration, we can use it. But now we know the molar concentration of the base, that is Cb. So if we are now looking for molarity of the acid, which is Ca, definitely we are left with the cover formula to use. So that's what we're going to use to calculate concentration of the acid in mole per dm3, that is molarity. Look at the formula. Just make your concentration of acid subject to the formula. Is that okay? Look at it. How do you do that? First, you cross multiply. If you cross multiply, then make Ca subject to the formula. It's going to be Cb times Vb times Na. Then divide it by VA and NB, which will actually be the coefficient of CA, you know. And that's what you have here. Next is substitute. You know the value is already CB is 0.4, VB is volume of the base 25, then NA, you know, 1 divided by VA. VA is the average titer, is that okay? That's average volume of acid used, 13.5, multiplied by NB, which is 2. Solve this out, you get 0.370 moles per dm cube. So that's the molarity of the acid. Finally, we are left with the mass concentration of the acid. Now that you know the molarity of the acid, that is the molar concentration of the acid, you can now use this formula to calculate the mass concentration of the acid. So look at the formula there, cross multiply. But anyway, substituting directly, molarity of the acid, we calculated it to be 0.370, equal to mass concentration of the acid, we don't know, divided by molar mass of the acid is 98. How did we get 98? Come here, this is the acid. Hydrogen is 1, you know, relative atomic mass of 1. Multiplied by this atomicity 2, you have 1 times 2, which is 2. Sulfur is 32. Add it to the 2, you're going to get what? 34. Then oxygen relative atomic mass is 16. 16 times 4 is going to give us what? There about 64. Then add the 64 to 34 you got, and you will now get 98. Cross multiply here, make mass concentration, subject a formula. If you do that, you get a mass concentration of this acid used for this experiment to be 13.26 grams per dm cube. And that is the solution to this problem.